and 0x80 is equal 0. This is my condition. And this is the code. Or I can write it while, like we did what we did with the if, not x and 0x80. Both are correct. This is what we exactly put in the if statement. So just you need to know, when do you want the condition to be true? Do you want it when the bit is 0, or do you want it when the bit is not 0? Now, if I want to wait until the bit is set, this means that I want the condition when the bit is 0. I want the condition to be true when the bit is 0. If I want to wait until the bit is clear, this means I need a condition that is true when the bit is 1. Is this clear? I think we spent a lot of time on this. Just 2 slides. So it's very important to know that you need to use a while loop with a semicolon, and then the condition will be based on what you want to do. Do you want to wait until the bit is set, or do you want to wait until the bit is clear? If you want to wait until the bit is set, then the condition needs to be true when the bit is 0. I'm repeating what I've just said before. And if you want to wait until the bit is cleared, then you need to wait. The condition should be true when the bit is 1. That we want to check. Right. Move to the next slide. You know, because we are using, you know, when we clear, we are using bit masks. You know, when you write long codes and you have multiple bit masks, it will be very difficult to follow your code. And even for someone who reads your code, it will be a bit difficult to check it. So we can use always the define. We can use words like this. So for example, if I want to set bit 3, I can write define set bit 3, and then I will put the bit mask next to it. And then in my code, I will just use the text set bit 3. So it's clear when I write this statement, it's clear that I want to set bit 3. So you don't have to work out. And this is, you know, imagine that port A is 32 bits. It's not just that you are looking for bit 26 or whatever. So it's always good to work with the define. This is just to make your code clearer. Again, I can use it here as well. While port A and set bit 3. So if I want to wait for bit 3 to clear. Again, this is good practice just to make your code, you know, clear and easy to read, easy to follow, and easy to understand. Last slide about bit manipulation is about shift operators. So the shift operators, as you know, shift integer values by a specified amount. So we have the left shift and we have the right shift, and we did this. I don't know if you remember for when we did with VGHDL. The right shift, we have 2 cases. It will depend on the number or the variable, if it is signed or unsigned. The left shift, it doesn't matter, signed or unsigned, we get always the, I mean, it's the same principle. When we do a shift, so for example, here, if I have I is equal short integer I, so short is 16-bit. Long integer is 32-bit. So we have if I put short integer, and by the way, when you put short and long, you can even remove integer, because by default is for an integer. Short and long work with integer. And then if I want to shift I by 4 position, I want to shift it left, I'll do a left shift by 4 positions. So if this is the original value, this is I. When I do shift, so I shift this direction by 4. We will have 4 empty positions in the beginning, so we will fill those with zeros, as you can see here in red. So the least significant bits are filled with 0. Is this clear? So this is regardless of the sign, integer or sign or unsigned. Right shift, it depends on the variable, if it is signed or unsigned. If it is signed, if it is unsigned, we fill with zeros. If it is signed, of course, signed and it's negative, we fill with ones. So basically, general rule, we fill with the value of the last bit in the case of signed. So unsigned is clear. We always fill with zeros. You see here, even if the last bit is 1, so in this example, I have unsigned, short, integer, I has this value, so the last bit is 1. Because I have f, so and for f, the last bit is 1. When I do a right shift by 4, I will fill with zeros, even if the last bit is 1. If it was 0, I will fill with zeros as well. I don't care about the last bit. I don't care about it if it's 0 or 1. Because it's the variable is unsigned, I will just fill with zeros. Now, if it is signed, as you can see in the last example, I didn't put signed in the last example, but you know by default is signed. If I don't put signed or unsigned, then it's signed. By default is signed. So when I do integer x, this means this x is signed. If I want it unsigned, I have to add unsigned to it. Now, this is signed, and the last bit, as you can see, is 1. Then the result is this one. We fill with the value of the most significant bit. So if the most significant bit here, which is 1, then we fill with 1, which means the number, this number is negative, we keep it negative. But assuming that this was 0, then we will fill with zeros. Because the number is positive, we keep it positive when we do the shifts. Is this clear? And again, I'm just repeating what we did in digital. This is exactly the same operator, is the same syntax. Right, and this is the last slide. So if I just run this as a quick test for this, you can see the what will happen. And of course, you can try this at home. I'm just trying to prepare the code here. I'll just share the screen of my laptop. Right, so I wrote this code. Unsigned short integer I 0x FFF. This is unsigned, and I did right shift, and then long I j. I declared it long here. Long is 32-bit, and I put this value. This is signed, and then I shifted by 4, and then I want to display those as hexadecimal. If I display them as decimal, you will get the first bit as positive, and the next bit you will get it, or the next value, sorry, the next number, j, you will get it negative. I want to display it hexadecimal just to know the bits, the bits that have been added, zeros or ones. So what do I get in I if I do this?
0x 0ff0, oh sorry, fff in the end.
0x 0ff.
F.
Okay, good. And then for j,
0x ff goes to the left. 00000f.
yeah, good. I think this is what we should get. So I'm running the code. And this is what we are getting. So the first one, as you can see, we don't see the first zero, right? FFFF is equal to 0 FFF. Yeah, so they don't, sorry, I don't know why it disconnect. Yeah, so I have FFFF, 3 Fs. So basically the result was 0 here, 0 FFFF. We don't get the 0 displayed, yeah? I mean, if the result is 1, 0, I don't get the 0 displayed, just get 1. And then for the second one, long j, as you can see, we have f here, which means 4 ones, because the last bit was 1. Because it's signed, the last bit was 1, so we filled with 4 ones. Is this clear? Disconnected again, but I think it's clear. We just showed you this. It's similar to the examples that I put in the slides. Right. I think that's it for this lecture. If you